Hello everyone, Mr. Fawcett here, and today we are talking about how to find limits analytically, specifically with functions that have removable discontinuities. So let me first give you a quick review of what a removable discontinuity is. It's a word you're going to hear thrown around quite frequently in the limits section of an AP Calculus class. A removable discontinuity is a function that is continuous everywhere except for one point. So let's just call this value x equals 3. Say this is 1. We'll say this is 4. So you can see that this function is continuous everywhere except x equals 3. And these are the functions we're going to be talking about how to find the limits of today. Now, if I just gave you the graph of this function, it would be fairly straightforward. You would trace the function coming in from the left or the negative side and trace it coming in from the positive side or the right side. And you would easily see what that limit is, right? It's equal to 4. It doesn't matter that the value of the function is 1 because we know that the value of the function doesn't have anything to do with what the limit is, right? We're looking at what the function approaches. That being said, today, you're not just going to be given graphs. You're going to be given functions in algebraic form. You may be given tables, and you may be given some graphs, but in general, we're going to be working with the algebraic form of functions like we see down here. So it's not going to be as easy as just tracing a function with your pen, your pencil, or your finger. There's going to be some other ways we have to approach these problems. But that being said, that's what a removable discontinuity is. It's where the function's continuous except for that one point. So let's look at number 1. It says find the following limit below. Use any method you prefer, but show your work. Well, the two methods we've looked at so far are tables and graphs. So you have two choices. You can try to create a table. You can create a graph. You can use your TI-84s or whatever graphic calculator you're using to do this, and then we'll discuss. So take a few minutes, see if you can create a table for this function or a graph, and try to figure out the limit of that function as x approaches 2. Okay, hopefully you've had a chance to do that after pausing the video. I am going to start off with creating a table for this function. I'm going to use my TI-84 software. The first thing I did, oops, I guess I got to get out of there. First thing I did was enter the function in my Y1. Then I go to my table set, which is second window. Now, we're looking at x equals 2. Right, so we need to find some values on the left-hand side of x equals 2 and some values on the right-hand side. Now, it doesn't mean that those numbers are going to be negative, right? If x equals 2, the numbers directly to the left of 2 are positive, as are the numbers directly to the right. So don't think that you have to have negative numbers in your table. What you do need to be aware of is you want to choose numbers that are very close to 2. So you don't want to choose like -5, -2, and +1 as your three values to the left-hand side of 2. Those are too far away from x equals 2, and the function could be doing some funky things that far away from x equals 2. You want to essentially have a zoomed-in picture of the function right around x equals 2. So you can see in my table setup, I'm going to start with 1.997. I'm going to increase by 1,000. Okay, you could start at 1.9 and then go to 1.99 and then 1.999. But you just want to make sure that your numbers are close to 2, the ones that you're looking at. So once you have that set up, I'm going to hit second graph to go to my table, and it spits out the values for you. So you could create this table on your own in the space provided, but again, we're just going to look at these values right here. And you can see as we get closer and closer to 2 from both the left and the right-hand side, we are approaching the same number. We're approaching 5. Okay, so it's pretty easy to tell that the limit of this function as it approaches 2 is equal to 5. And again, it doesn't matter that the function is defined at x equals 2. It just so happens that it is in this case. But we don't have to look at that, right? It's irrelevant what this row is. We just have to look at what's going on from the left and the right. Okay, let's look at a graph real quick. in case you did that representation. So if I click on graph, and I actually already had this zoomed in, but let's look at zoom standard first. And we're looking at, again, at x equals 2 and what the function's doing around there. We're going to need to zoom in here, I think, to get a better picture. You don't have to zoom in blindly, right? You can go to Window and create the specific window that you want to see. So maybe I want to go from x equals 1 to x equals 3. And I'm going to go, I know that my limit is 5, so I'll just go from 0 to 10. And let's see what that gives us. Okay, so remember I started at 1. Let me get out my pen. So this is really 1, right? This is 2, and this is 3. So if I come up here, I'm looking at what the function is doing at this point. As I come in from the left and come in from the right, we can see that we are approaching 5. Okay, so either way you do it, either the table or the graph, it should give you a pretty good idea of what the limit of this function is that it approaches 2. But we should be comfortable either way if I asked you to give me an example of either a graph or a table. Okay, let's get back to the notes. Number 2 says, try to see if you can find the answer to number 1 without using a graph or a table. So maybe there was a way we could have figured out the limit without actually drawing out a table, without drawing out a graph. Take 30 seconds to think. We sort of touched on it in our discussion, but I didn't specifically lay it out for you. So take a few seconds, see if there's a shortcut you may be able to figure out. Okay, so maybe you noticed that the value of this function, so let's call this function f of x. And if you looked at the actual value of f of 2, if you substituted that in, that should have been equal to 5, which was the value of the limit, correct? I know that we've said before that the value of the function at that x value has nothing to do, or it doesn't influence what the limit's going to be. However, there are times where it becomes a nice, easy shortcut. So this work right here, probably easier than writing out a table or drawing out a graph to find the answer to this limit. But we also need to be sure that this works every time, or we need to know when this will work and when we actually have to use a graph or a table. So let's jump to the next page to look at when we can use this and when we can't. So here's our theorem. Here's our important theorem for the day. If f of x is continuous at a, then the limit of f of x as x approaches a is equal to f of a. A lot of times when we just use variables, it may be harder to understand what the theorem is. So let's break it down into more a visual example. I'm going to go all the way to the end where I have some extra room. Okay, so I'm going to give you 3 graphs actually, and then we're going to talk about how they model what that theorem up there stated. So if the function is continuous at x equals a, then we can say that the limit of the function at x equals a is equal to the value of that function at x equals a. So let's just come up with 3 different graphs rather. And they're going to look the same except for just a couple of key differences actually. Label some axes for you. Okay, And let's say the question here was trying to find the limit as x approaches 5. We'll call this function f of x. We'll call this one g of x, and we'll call the other one h of x. So we're trying to find the limit of f of x as x approaches 5. And right, if we had the graph in front of us, we could just trace it. And we could pretty easily see that the limit is equal to 4. But what we also notice is that the limit is also going to be equal to the value of this function at x equals 5. So this limit is equal to f of 5. And this is because the function is continuous at x equals 5. If we go over to g of x, and we want to find the limit as x approaches 5 of g of x, okay, well, we could trace our function as we approach 5 from both sides. But notice that this is also equal to 4, right? The limit's also equal to 4, but that is not the value of g of 5, right? Because g of 5 is actually equal to 1. So this is not a true statement, but it's because the function is discontinuous at x equals 5, right? So it does not fit our theorem from above. And let's take a look at our very last example. So again, I'm trying to find the limit this time of h of x as x approaches 5. Well, let's approach 5 from both sides. Notice that that limit is also going to be 4. And we also know that g of 5 is 4, right? So, sorry, h of 5, goodness. Need to make this h down here as well. But the question is, well, this function h of x is not continuous everywhere. It's discontinuous at x equals 7. Well, if we go back and look up at the theorem, right, it said that the function had to be continuous at x equals a. So it just has to be continuous at the point we're looking to find the limit at. Okay, so it is continuous for f of x at 5. It's not continuous at g of x for 5. That's why this does not work. That's why this is this equation is not true. But for h of x, even though the function is discontinuous elsewhere, it is continuous at x equals 5, and that's all that matters here. All right, so I just want to make that clarification because you may have questions about it as we move through the lesson. If you have questions about what we just did, again, feel free to rewind the video, watch it 1 or 2 more times. I am going to erase this, and we're going to go back up to some more practice problems. So again, if f of x is continuous at a, then the limit as x approaches a of f of x is equal to f of a. So again, all this is saying is that if the function's continuous at that x value, the limit is going to be equal to the value of the function at that point. So all we have to do is substitute in the x value to find value of the limit. So no graphs, no tables are needed. We can strictly use substitution as long as the function is continuous at a. All right, you guys have a few problems below to try out. Again, pay attention to what I just underlined. Make sure the function's continuous at a if you're going to use the substitution method. Otherwise, you may need to try another method. Once you're done with that, we're going to hop down to the bottom of this page, I believe, and start talking about some removable discontinuities.